So the idea, the clinical impression that you have as a clinician is that this is very valuable. But as I said, I came from the field of the autosomal dominant ID. I did my PhD here, and I worked with them for several years in biomarker research. The numbers look very similar. And here, what I want to say is that in red, we have many studies with Down syndrome. In blue, we have many studies in autosomal dominant AD. And here, the dots, as you can see, are basically the same. And this is saying how the coefficients of variation, the span of symptom onset, the prediction intervals, essentially we're seeing how much the presentation changes with respect to age. And as you can see in red is people with Down syndrome. And this bar is no greater than the others. And this has huge implications because it means that the way we should analyze the data in Down syndrome should be very similar to autosomal dominant AD. The statistical modeling, how we should analyze the data is completely different. And you'll see that all this I'm explaining will apply directly to APOE4 homozygotes. This is the paper, the first paper that we published in 2020, in which we could show the natural history of the AD biomarker changes. And here what you see is euploid control, so the general population, no Down syndrome in blue, and people with Down syndrome in red. And you can see in the x-axis is decades. It's very small, but this is 20 years, 30 years, 40 years, 50 years. And you can see that decades before symptom onset, the dotted lines, decades before, we can see dramatic changes in several AD biomarkers. And we can establish a sequence of events. And if we do that and we color code the biomarkers in the main categories, so those in blue, those in amyloid, in green, those referring to tau, and in yellow, those of neurodegeneration. The point I want to make is that the models, and we analyze the chronopathology, how the disease unfolds across the lifespan, you can see that the chronopathology, this unfolding of the disease, is extremely similar in Down syndrome and autosomal dominant AD. So now you'll see that the Nature Medicine paper is essentially recapitulating these several studies and dozens of studies that we've been publishing in Down syndrome and applying those studies, this view, this prism to APOE4 homozygotes. So the first thing I need to say is that in order to do that, you need huge numbers. And this has been one of the main reasons why it took us so long to do this paper. The idea that APOE4 is very important for Alzheimer's, and a lot of the data was out there. And as Dr. Ashford mentioned, many of the individual ideas were already there. But what we were lacking, and we managed to do, is to gather very, very, very large numbers that weren't just there, easy to gather 10 years ago, for instance. So just to give you an idea, in the pathological study, in the NAC database, we collected over 3,000 individuals, and we analyzed the AD pathology. The AD pathology by haplotype. This database is composed largely or to a great extent of people with dementia and MCI. This is important. There is a bias towards people that have died with symptomatic Alzheimer's disease. So we see more pathology than we would see in the general population. But even though, if we analyze the people that died there and are analyzed in the NAC database, you can see that in red is the high, very important AD pathology, intermediate, that is also considered very consistent with AD pathology, and in this kind of bluish or purple colors, no or very low pathology. You can see that there is a huge difference between APOE4 homozygotes and APOE3 homozygotes. There is a lot more AD biology and happening earlier than in APOE homozygotes. And the other thing that we needed to do is to gather an even larger number of individuals clinically in the clinical cohorts. We needed to gather 5 of the largest cohorts in the world to really be able to collect over 10,000 individuals. Just imagine the effort was for all the PI, the family, and those clinicians across around the world. And here what we did is analyze not the pathology, but the biomarkers. So in the left lower panel is the amyloid markers, in the right lower panel, the tau markers. And you can see again in the apoE homozygotes in red, and in blue, sorry, in green, the apoE3 homozygotes. So you can see that as a homozygote age, almost all of them accumulate amyloid and accumulate tau, such as that by age 80, they basically all of them have amyloid and tau. And this is what why we said in the paper that there is a near full penetrance of AD biology in these data sets. We'll discuss about this, the representativeness of these data sets. But there is a near full penetrance of AD biology in apoE homozygotes, as demonstrated by the pathological part of the study and the biomarker part of the study. This has already been shown. This is basically replication of previous replication or demonstration again of the replication, yes, of previous works that basically, as Rosford said, ApoE4 homozygotes have not only a much higher risk of developing the biology and the symptoms, but also at earlier ages. So that doesn't matter if you look at symptom onset, MCI onset, AD dementia onset, or death due to Alzheimer's disease, the homozygotes tend to be much younger than ApoE3 carriers. But if we do two homozygotes, and this is completely new data, to my knowledge, this hadn't been assessed before, and we say, okay, all the people that in the NAC database that develop AD symptomatology, AD dementia or AD MCI, and we analyze how variable is this disease onset. And we create the 95 prediction interval the same way that we did it for Down syndrome. You can see that ApoE4 homozygotes have clearly smaller bars than ApoE3 homozygotes and very similar to this genetic form. So let me plot it in a different way. So we are again plotting the prediction intervals, and you can see that DSAD, presenting one, and ApoE4 homozygotes have very similar prediction intervals. So the variability around symptom onset, which in ApoE4 homozygotes is age 65, similar for symptom onset, not MCI and dementia that we'll have it later. The similar variability as in the genetic form of Alzheimer's disease, and a clear gene dose increase in these prediction intervals when you have you are heterozygote or homozygote, ApoE3 homozygote. So again, similar predictability of disease onset with respect to AD or DSAD. And what about if we look to the biomarker changes? And let me emphasize, and this is the merit of the PIs that were so generous to share the data. Every dot here is a participant, is an individual that really contributed with his or her time, effort to these studies. And just imagine how many lumbar punctures, for instance, or how many PET scans. There is a huge effort behind this slide. And here what we're doing is basically the same, is putting the age in the x-axis and the biomarker levels in the y-axis. So we're seeing here 4 decades, basically. And you can see that ApoE homozygotes, heterozygotes, and non-carriers have completely different trajectories with respect to the timing of the biomarker changes. Very, very different, in a very clear gene dose response. And if we do the modeling to assess the chronopathology, or again, how the disease unfolds in ApoE homozygotes, and we color code that, you can see that the trajectory of the biomarker changes, the temporality of when these biomarkers change with respect to the predicted age of symptom onset, and this again was something new, is very, very similar between homozygotes, DSAD, and autosomal dominant AD. So striking similar temporalities for the biomarker changes in all forms of genetically determined Alzheimer's disease. So if, and this is a summary slide for this part of the presentation, if we apply the Alzheimer's Association criteria that defines the disease biologically, then yes, we can say that yes, APOE4 homozygotes have near full penetrance of AD, at least in these selected samples. That yes, there is a predictability of AD symptom onset to the same level as the other forms of Alzheimer's disease. And yes, there is a predictable sequence of AD biomarker changes in this population that is very similar to that described in Down syndrome and autosomal dominant AD. So yes, I think that these three core characteristics of genetically determined AD are met if we apply the Alzheimer's Association criteria for the disease. So where are the areas of controversy? That is a valid controversy. There are several points that are very, very valid. So let me identify some areas of controversy. And here, let me, if you're interested in a very clever editorial with very, very valid points, I would recommend you reading this editorial in JAMA Neurology by Eric Raymond, who is an amazing scientist that has worked with also autosomal dominant AD in Colombia, with APOE for many decades. He's made tremendous contributions. And this viewpoint, he was a bit, he raised several valid points criticizing, I wouldn't say, or signaling areas of controversy with respect to this proposal. And let me also cite a reply after we published the Nature Medicine paper. There was another an editorial or a comment to our paper, and we had a chance to reply. So some of this controversy we've contributed in written, so to speak, and some of the responses to several of these points we published a few weeks or months after the publication of the paper. So first of all is the clinical penetrance, as I said, because it is clear that lifetime risk estimates vary and that not all APOE4 homozygotes will develop NCI-early dementia. This is very clear. Also, another very important point is the racial differences and the selection bias that we might have, and the lack of population diversity in the study, which is very, very clear. This is a problem that we have in AD research in general. So basically, most of the research so far has been done in the US and Europe with people of Caucasian descent, of European descent, and we really need diversity, and you'll see that this can be very, very important, specifically in this area of research, and so we really need population-based longitudinal studies, especially those including diverse racial, ethnic, and geographic groups, because things can be different. And I'll show you some of the results. And then there was some controversy about the modifiers. The idea is that in genetic determined AD, it's true that when you have such a strong driver, the modifiers have less power to modify the disease to a certain extent. Or at least this is something that some people have raised significantly when analyzing our proposal of reconceptualization of APOE4. So let's dive into some of these issues. So first of all, does a mutation need to be fully penetrant clinically? And I'd argue no. I think this is something that in Alzheimer's we've come to believe because our model for genetically determined AD has been autosomal dominant AD, this presenilin 1, presenilin 2, and APP mutations that do have full penetrance, clinical penetrance. But let me just look outside of neurology, for instance. And if you take, this is a very well-known mutation, no? The BRCA1 and BRCA2 mutation. And this is the risk that they confer for breast cancer, for ovarian cancer, and no one discusses that this is a genetic cause of cancer. Actually, many women take out their breasts if they have these mutations in order to avoid developing cancer. And I have to say that we did not, because we could not assess the clinical penetrance of the disease in our study because of the selection bias that we have in the people that were more towards the symptomatic stage of disease, and the clinical cohorts, the opposite. They were more cognitively healthy.